Welcome to this next session. This is going to be the more or less the last lecture on kinetic theory of gases, which will be extension of whatever we have done previously. That means we had talked about the collision frequency. We are going to extend that today to effusion and to understand how are they going to be used when we are having a practical application. So, what we are looking into, we have talked about the collision previously, but what we need to understand that if we are having a collision, then there is another term which is associated with collision, that is the mean free path. What is this mean free path defined as? You see the molecules are randomly moving in all the three directions, and their direction is in all x, y, z direction possible. So, these random movement of the particles, they are all colliding randomly, that we have already discussed in the last class. What is the collision frequency? That means the rate of collision of a particle per unit time. So, the collision frequency also was discussed, as was derived in the last class, is something like this. Okay. So, what we have after collision, what happens? When you have two molecules collide with each other, the average distance they travel between the successive collision is called another very important term, which is a parameter which determines a lot of gas properties, is a mean free path. So, the average distance a molecule travels between successive collision is called the mean free path, and usually represented by a lambda. Once we have a collision frequency, we can calculate the mean free path, the average distance a molecule travels between collision. So, if we know the collision frequency, we can relate that. If a molecule collides with a say frequency with a frequency z, that means that is the rate at which they are colliding, that is the frequency number z, the collision frequency. So, if the number of collisions molecules is colliding is z, it spends the time in the free flight between collision can be given as 1 by z. Did you understand what I meant? A molecule collides with suppose a molecule collides with a frequency z, means they are colliding with each other at the frequency means at the rate, okay, how many times it is occurring. So, if the number of times the collision are occurring is z, then it spends, what is the amount of time it spends? That it spends 1 by z time in the free flight between the collision. Did you understand? So, the time spent in the free flight is 1 by z. Okay. So, if time spent in the free flight is taken to be 1 by z, then what is going to be the distance travelled? If they are moving with a mean velocity c or v bar, then time is 1 by z, then the travelled distance should be velocity by time. So, velocity by time, it is going to be z into 1 by z into the average velocity. Or you can look at this otherwise, the collision frequency z is equal to the collision made by one molecule in time t divided by unit time, that is the rate of collision, into the total number of molecules present in the volume which is considered. So, this is what we had derived in the last class. This is the total volume which is associated with the total number volume present in the total number of collisions will be the number of molecules within that volume per unit time into the total number of molecules present in that total volume of container. So, this is the volume which is going to be swept. This is the cross sectional diameter collision cross section area, that is usually given by pi by d square, into this is going to be the length of the tube through which it is going to sweep. So, a molecule with diameter d will sweep a volume corresponding to this. This is the pi d square, and this is the distance of the, since they are traveling with the relative speed, mean relative speed of CRL. So, it should be CRL into delta t is the total length of the tube. See, now the tube which we had taken is imagined is going to be a straight line, but in reality this shape of the tube is going to change, okay, because the collisions are happening continuously, and whenever we are doing a calculation, we are imagining the tube is a fixed point with a fixed diameter cross section area of sigma, which is equal to pi d square, where d is the diameter of a molecule which is sweeping the volume of a tube. Okay. So, we have to imagine that the tube is fixed, but actually it is going to be always changing and not having a definite orientation, because the collisions are happening randomly. So, what we had derived in the last class, we had derived the expression for collision frequency, which is given by this. Sigma is the collision cross section area into the average speed of approach, or mean speed of relative mean speed of approach of one molecule with the other towards the other, and this is the number density. Okay. And the number density we had further simplified into number of moles into Avogadro number divided by volume, and this volume we had replaced by the ideal gas law equation, P V equal to nRT. So, the volume was replaced by nRT by V P. So, this is how we got this expression. Okay. So, this was the last class which we had discussed. Now, what we are going to see how to derive the expression for mean free path. So, mean free path is related to the diameter of the molecules and the density of the gas. Okay. Now, we have to derive and see how it is going to happen. We assume the molecules are of spherical shape with diameter d. Two molecules will collide, only collide when their diameters are in particular distance between the centers of the two molecules. That means no two molecules will collide unless their path are less than a distance d apart as the molecules approach each other. When if we are assuming here all the molecules are having the same diameter of d, and their minimum approach distance becomes the diameter of the centers from one molecule to the other becomes the d distance apart. So, they should be less than d, only then you have undergoing collisions, and the mean free path lambda is equal to the average distance. Okay, the mean free path is equal to the average distance traveled in a unit time divided by the total number of collisions that occurred in that time interval. Okay. So, please understand this. I am going to read it again. The mean free path lambda is defined as the number the average distance. Average distance is going to be what? Velocity into time is always going to give you the distance. So, the average distance is going to be the average velocity into time interval travel, that is the equal to that, and in time delta t. So, the average distance travelled in time interval delta t divided by the total number of collision occurring in that particular time interval. Okay. So, this is what we can write. The average distance travelled, this is the average velocity into the delta t is going to give you the distance in per unit time, that is by delta t, divided by the collision occurring in frequency of that particular collision number of collision occurring in that particular time interval, which is nothing but the collision frequency. Okay. So, if you remember the collision frequency expression, we had something like this: sigma the relative mean speed into pressure divided by kT. This the K is the Boltzmann constant, T is the absolute temperature. Okay. So, again if we rewrite from the expression we know from the previous page. If you see, we have defined this as the distance travelled between consecutive collision, which is the mean speed divided by the collision frequency. So, if we do that, we redefine this. We have defined collision mean free path somewhere like this, and that is coming to be from here also you will see it is coming to be the mean speed divided by the collision frequency. The mean speed I keep it as it is, and then I say Z is what? I replace the expression for Z, whatever I had derived in the last class, I put it here. Here sigma RL into the relative speed of the approach of the molecules into pressure, and in the numerator goes the kBT. Okay? Kb is the Boltzmann constant. Now, you see what is the expression we had derived for the relative mean speed. Relative mean speed is defined as under root 2 into the mean speed. So, I replace the relative mean speed of approach by the mean speed, and I get a under root here. So, this is going to cancel off, and then what you are left with is a expression in terms of kT by under root 2 sigma pi. What is sigma? Is the collision cross section area that is equal to pi d square, where d is the diameter of the molecule, or we can say if they are identical molecules, it is the diameter of the molecules, or we can say it is the distance between the two centers of the molecules, and within this center only if the molecules are going to fall, they will undergo collision. Please always remember, in each of the slide I am writing, in various times I have used V or C. The V and C, whenever they are without any subscript, are meaning the same. When we say that V rel or V say mean, that means I am also meaning that is the C term. Sometimes it is not actually right that we use different types of terms, but it happens that some books write something, some books write V, some book write C. So, that is why in each of the slide I have mentioned, whenever you are seeing a V without any subscript, is actually the same term as V, and they are all meaning they are movement of the particles in the 3 dimension. Unless we have a subscript x, y, z, where they do not mean the velocity along any particular axis. Whenever we are talking about V, C, that means we are always talking about the velocity, which is supposed to be the result of a radius which we have drawn on a say spherical surface with radius V in a 3 dimension when we were calculating the what do you call distribution in speed. Okay. Please remember this, the V and U, V and C are always identical, and I have also mentioned them in each of the slides. Another alternate way of deriving the mean free path, if you have understood one, that is sufficient, but you can just look at it. Mean free path is the inverse of the collision frequency, again the same thing which I am writing. Inverse of the collision frequency means 1 by z into the distance travelled. Again, what is this distance travelled? Distance travelled is c, where they are moving with the velocity average speed. So, c is the c bar is the speed, or v bar is the speed, into delta t is the distance. Okay. So, the mean free path is the average distance travelled by unit time, volume of interaction, when the volume swept by the molecules in unit time, into the number density. If you are putting that, this is the distance travelled per unit time, this is the interactions occurring per unit time into the number density. here this is the number density, this is the number density, that means the total number of molecules involved. This is the collision per molecule. We multiply that by with the total number of molecules present. So, that gives us the number density. Now, we replace the C-rel with the expression for the mean speed. The relative mean speed is going to be equal to under root 2 the mean speed. So, if you replace that, you again get an expression, another very interesting expression. If you keep breaking and reforming the expressions, you get they are the same terms, you remember, but you are writing in different form, 1 by under root 2 sigma, and this is the number density. Number density is number of molecules per the unit volume of the container. Okay, and see, this is pi, and the sigma is the collision cross section area, that is pi d square. So, the mean free path, if you see the expression here, what is the expression for Z, what is the expression for C, and what is the C means the mean speed, not relative, that it is the mean speed of approach or mean speed with where they are traveling. It is not the rel speed here, not relative mean speed, but it is this mean speed which we are talking about. So, if we are talking about the expression for lambda, just have a look, please keep remembering only this expression, so that you can substitute for each of the term and understand what happens. In this, you are having pressure in the denominator. So, if you are doubling the pressure, what will happen? The mean free path should be reduced by half. Okay, they are inversely proportional. So, if you are double the pressure, then the mean free path should be becoming half. If you are looking into the typical mean free path of nitrogen molecule at 1 atmosphere, it is going to be around 70 nanometers, around say 10 to the power 3 molecular diameters. Although temperature appears in the expression, if you see, in a sample of constant volume, suppose the total container is fixed, the pressure is going to be directly proportional to T. You have the ideal gas laws. When temperature, the volume is constant, then the pressure is directly proportional to T. Okay. So, if the pressure is, if the volume is constant, okay. So, if the volume is constant, though the temperature is appearing in the numerator, so the increase in pressure should increase the mean free path, but since for a constant volume, if you have a constant volume, pressure increase is going to be proportional to the temperature increase. That means T by P will remain a constant. When the temperature is increased, the P will also increase. So, if this is the condition, then you see this will have no effect on the lambda. Both are, if we are both are going to, if you are having P proportional to T, that means change of P by T will not be affecting, they will be remaining a constant. So, the mean free path is independent of the temperature for a fixed volume of a container, because in spite of the fact that temperature is appearing directly in the numerator. The distance between the collision is determined by the number of molecules present. Okay. So, if there are number of molecules are more, they are going to be colliding with each other more frequently, and the distance they need to travel is going to be less. Okay. So, the number of molecules, the distance between collisions is determined by the number of molecules present in the given volume and not necessarily by the speed. So, in spite of the fact that speed is there in the expression, so it is not that the speed is going to be the determining factor, it is the number of molecules which is present in the system is going to determine whether the lambda, the mean free path is going to increase or decrease. So, in mean free path thus increases with the number of molecules per unit volume, increases as the number of molecules per unit volume decreases. Okay. If the number of molecules are less, they have to travel a longer distance to encounter each other. Obviously, that means you have to have a lambda which is going to be will get bigger and bigger. Okay. So, it is not dependent on the speed, but on the number of molecules, and it is independent of the temperature for a constant volume system. And for if the pressure is double, then the mean free path is going to be halved. Okay. Now, so if you take a look at the nature of dimensions of what we are talking into, if you see the perspectives of molecular path, mean free path compared to the average molecules of, you have the average distance between two molecules, okay, and the diameter of a single molecule. If you are comparing in that order, then you see these are actually not to scale, but you can see the mean free path is, this is a collision, this is another collision, okay. But if you are looking at this, the mean free path is almost around 310 times the atomic diameter and 28 times the average molecular separation. That means, if you are seeing the you see the ratio in which we are looking into, you have the molecular size compared to the average molecular separation. Okay. What is the molecular size? The atomic diameter is around this and the molecular separation is 3.3. So, the average molecular separation is 10 times that of the atomic diameter. Okay. The separation of two molecules is around 10 times that of the diameter of a single molecule. But when we are comparing that with that of the mean free path, that is the collision, the distance travelled between the collision is far more compared to that of the diameter of the molecule or the distance between the two molecules. Okay. So, now the next thing should be, when we are talking about collision, we have talked about the mean free path. The next important which is important in understanding the transport properties associated with the gas phase, is to find out the rate at which they strike a area, okay, a imaginary area which can be in a gas phase or a real wall. So, for this which we are going to be looking into, we are looking into a flux. What is the flux? Flux is the number of collisions with a particular area A at a given time per the unit area which we are looking into. Okay. So, the collision flux is the number of collisions with the area of interest A per unit time divided by the area into the duration of the interval. Okay. So, in other words, we can write it is the collision frequency. This is, you can see that the number of collision occurring on area A at unit time. So, this is the collision frequency divided by the area of interest. Okay. And this can be derived. I am not looking into here, the expression is given, but we are going to derive that. Okay. So, the collision frequency, if we want to find out, it is nothing but the collision flux multiplied by the area, right. So, the number of collisions or hit per second is obtained by multiplying the flux by the area of interest. Okay. Now, let us look into this. This is something which we had talked about in previous classes. Now, you see we are not looking into 3 dimension. We are looking of the molecules moving in one particular direction, in which direction we have the wall and the area of interest in that wall. Now, let us consider a wall of area A perpendicular to x. Suppose this is the direction x and perpendicular to that we have the wall. A molecule with speed travelling along the direction x is supposed to be Vx is greater than 0. That means it is travelling in the positive direction towards the wall. It will strike the wall within an interval of delta t if it lies within the distance dv v delta t. Okay. So, if they are moving with this velocity in this direction, then what if this we have done before also, then in interval delta t, which are the molecules which is going to strike the wall? Only the molecules which is going to have be at a distance v delta t. V delta t is the distance, and what is the area? Area is this. So, the total volume which is going to be in this zone is going to come, and all the molecules within this volume will have the chance of colliding with the wall A. Okay. So, the total number is going to be volume, total volume is going to be the distance into the area. Distance is the velocity through which they are travelling, v, into the time interval t. The velocity into time interval gives you the length. So, therefore, all molecules in this area, in the volume this, with positive x component of velocity will strike the wall at interval delta t in time delta t. The total number of collision in this interval is therefore the volume into the number density. So, total number of collisions will be always the total number of molecules present moving towards that direction into the number density, because we are always talking about one collision into the number density. The total number of collisions in that interval will be all the molecules within this area, within this volume into the number density. And what is the number density? We represent the number density by Nv, which is nothing but number of moles per unit volume of the container. So, to take account of the presence of the various velocities, because velocities can in the sample which can result, some will have higher velocity, some, because you know that velocities are having a distribution. So, we have to take all the ranges of velocity into account. What we need to do to take account of all the possible velocities, what in the sample, we need to sum over all the positive values of the velocity weighted by the probability distribution. That means, to find out the total number of collision, what we need to do, see, total number of collision we are finding out is the total number of molecules present which is going to strike in this wall into the total number density. Okay. That means, distance, whatever molecules are present here into the number density gives you the total number of collisions which likely to occur. So, the total number of collision is number density into area. Just have a look what we are looking into. Total number of collision is this. Okay. Now, we are going to look into that. We are going to sum it over all the positive values of x and into weighted by the probability distribution. When we are looking moving in only in the positive direction and in the x direction, we integrate. The x was this side, v was this side, v delta t was the term which was outside, we have taken the v inside. So, velocity into the distribution function gives you the weighted fraction. So, let us find out what is this going to be, and what is, if this is the collision number of collision or collision frequency, then what should be the collision flux? Collision flux is going to be number of collision divided by A and delta t. Okay. So, let us see what is going to be the collision flux. If this is the number of collision, then divided by A delta t. So, this is the number of collision flux which we are getting. Okay. Now, look into this. What we have looked into, we have simplified this. We are not looking into this part, we are just looking into this part. Okay. When we are looking into this part, we put this value of the one dimension velocity distribution. If you remember, the 4 pi term is not 4 pi term which is supposed to be v square term is not there. So, this is the term which is coming from the normalization, and this is the exponential term. Okay. So, if you look into this, it is v into the exponential term. So, what we are getting? We are getting this function, something similar to what we are having as a standard integral. See, this is what we are getting, and this is the standard integral. When we compare these two, what should be n? N should be 1, right? And what should be a? A should be this term, that is m by 2 kt. Okay, k is the Boltzmann constant. So, if I compare that, this expression, if I have n equal to 1, then the solution of that differential integral is 1 by 2a. So, if I put the 1 by 2a, what do I get? I put the values in the expression of 0 to infinity here, okay, in terms of this, and this term I am replacing by 1 by 2a. So, this is my 1 by 2, and this is my a. Okay, this is my a. Okay, clear? So, I get kt by m. So, if I get the whole expression, I can rewrite the number density or the collision flux as this, which we have evaluated to be this. I have multiplied for this one, we have multiplied by this, because this was the term which was previously there, the normalization term, the constant term. So, this was added, multiplied by this. So, what you get it? You get here is this value, you simplify this, you get something like this. Now, you can put in various forms of that. So, collision flux can be derived as this. Now, you substitute for the value of c, velocity, the mean speed, and you can get some simplified to in terms of this, or the number of molecules per unit volume, the number density. If you are applying this, you can use this. If you apply all these, you get this very simplified. It is not very difficult if you understood this part, others are only simplification. Only other thing is the rate of effusion we need to understand, and this is probably going to give you the last section of the discussion. The empirical observation on effusion is summarized by Graham's law of effusion, which states the rate of effusion is inversely proportional to the square root of the molar mass. What is effusion? Effusion is when you have a gas particle moving through a hole, the rate at which it is going to pass through the hole. So, it is going to depend on the number of times it is going to strike that hole. So, actually it is going to be related to the collision on the wall, okay, and this wall does not have an area, it has an area, but it does not strike and come back, it passes through. So, the rate of effusion is inversely proportional to the molar mass, was what was given by the Graham's law of effusion. This results from what? That we have already got the kinetic model. Now, we know that it results from the term, all results from the mean speed of the molecules being inversely proportional to the mass. Okay. The speed at which they are going to be moving is going to be related to the rate of effusion, and that speed is actually related to the expressions, if you remember, is inversely related to the molar mass. So, since c is inversely proportional to the molar mass, the rate at which they are going to be escaping is also going to be related to the molar mass. Therefore, rate at which the molecule strikes the area of a hole should be inversely proportional to the molar mass. More detailed expression of rate of effusion can be obtained from the rate of collision, and hence the effusion data can be effectively used. Okay. So, when the gas of say pressure P and temperature is separated in a vacuum by a small hole, something like what I have shown here, there is one hole through which the gas can pass. Rate of escape of molecules is equal to the rate at which the molecules are striking that area. So, once we know the collision flux, that means the number of hits the particle is making on the particular area divided by area per unit time, then we get the can calculate the rate of effusion. So, the rate of effusion through a hole of area A naught is going to be nothing but the flux, the collision flux into the area. That means, this is actually the rate of collision. Whatever is colliding, rate of collision is actually equal to the rate of effusion, and which is nothing but the collision flux into the area. And collision flux we have derived is this, and this is the area of interest. So, if you rewrite it, you can replace the small m with the big M, kT can be replaced by m, and then you get a Avogadro number in the top. So, if you please remember the relationship between n, k and r. K means k and then Boltzmann constant. The effusion rate for a gas depends directly on the average velocity or speed of the particle. Thus, faster the particle is going to move, more likely they are going to escape or pass through the hole. Okay? Thank you so much.